We will be talking a little bit more about Euclid's algorithm, an algorithm that we described in a previous video. Okay, so just a quick reminder, this algorithm takes two natural numbers a and b. Let's say they are different from 0. Okay, and what we do is we divide a by b. Okay, we do a division with remainders, so we can write a as q1 times b plus a remainder of r1, where r1 is in between 0 and b. Okay, now let's assume that r1 is different from 0, and then we take b and r1, we divide b by r1, again with remainder, and so we get a quotient of q2 and the remainder of r2, and we keep doing so. Alright, now on purpose I wrote a little bit more of these divisions towards the end of the algorithm. Actually, we proved that the algorithm has an end, and what happens is at the end of the algorithm, this last remainder that's different from 0, we proved that this is actually equal to the greatest common divisor of the numbers a and b. Alright. So now, okay, on one hand this is very useful because it gives us a way of finding the greatest common divisor of two numbers. Now, let's take another look at this algorithm, and actually what we can do is we can go back into this algorithm from the really last division that gave us a remainder that's not 0. So that division gave us the GCD. Alright, and here's what we can do. How about we take this term here and we move it over to the other side. Okay, so what we get is that, the remainder rk plus 2, which actually is the GCD. So let's write down the GCD of these numbers a and b. Alright, is going to be equal to rk, right? So again, we're going to move this term over to the left hand side. So we get rk minus qk plus 2 times rk plus 1. Alright, so again, all we did is we moved one term of this expression on the right hand side of this equality over to the left hand side. So nothing special. Alright, now let's move back up to the previous equality that is part of the Euclid's algorithm, and let's do the exact same thing. Let's move this term over to the left hand side of the equality. Alright, so what we get is a way of writing the remainder rk plus 1. Alright, and how about we replace that expression of rk plus 1 in here. Alright, so we are going to get this is equal to rk minus qk plus 2 times, and instead of writing rk plus 1, we get rk plus 1 from here. So instead of writing rk plus 1, we are going to write rk minus 1 minus qk plus 1 times rk. Alright, so again, just basic algebraic manipulation from one side of the equal sign to another side of the equal sign. Alright, now let's break these brackets here. So this is going to be equal to rk minus qk plus 2 times rk minus 1. Minus with minus gives us a plus, plus qk plus 2 times qk plus 1 times rk. Alright, again, complicated notations, but just basic algebraic manipulation. Alright, now when I look at this expression here, alright, I see rk appearing here and rk appearing here. Alright, so we can factor rk, so let's do so. So this is going to be equal to rk times what's left from this occurrence of rk is just 1, and what's left from this occurrence of rk is plus qk plus 2 times qk plus 1. Alright, and we close the bracket, and there is this middle term here left, minus qk k plus 2 times rk minus 1. All right, so again, just basic algebraic manipulation, and let's see why this would be of any interest to us. Okay, if we get back into what we did, so we started off with the greatest common divisor of the numbers a and b, which we took from here. All right, and if we look over to the right hand side of this equal sign, we notice that we wrote this greatest common divisor as a combination of rk and rk plus 1. All right, and they are the previous two remainders of Euclid's algorithm. All right, and then we did a little bit of an algebraic manipulation on here, and in the end we came up with this slightly more complicated expression. But what we have to notice now is that this last expression that we got is a linear combination between rk and rk minus 1. All right, so basically this little manipulation here allowed us to write the GCD of a and b not in terms of rk and rk plus 1, which are the previous two remainders in Euclid's algorithm, but in terms of rk and rk minus 1. Okay, so sort of we moved up the chain of these divisions one step. All right, now guess what's going to happen if we actually replace rk from this equality in here. All right, just like we did with rk plus 1 at the previous step. Okay, maybe we can stop the video for a second and think about what will happen if we replace rk from this equality by rk minus 2 minus qk times rk minus 1. All right, so actually what will happen is we are going to get an expression of the GCD of the numbers a and b not in terms of rk and rk minus 1, but actually in terms of rk minus 1 and rk minus 2. So we move up the chain one more step. All right, and if we keep doing so, all right, if we keep doing so, we are going to get a very nice result that will tell us that actually GCD of the numbers a and b is a linear combination of a and b. All right, and this is a very, very important result that will be used fairly heavily in number theory. All right. Now, for the eager student, maybe, take some numbers. I don't know, I used 75 and 18 in a previous video. Take some numbers like 75 and 18, compute their GCD, and show how the GCD of 75 and 18 can be written as a linear combination of 75 and 18 using only this process. So write down Euclid's algorithm, then go back up the chain of these equalities and figure out how the GCD of 75 and 18 can be written as a linear combination of 75 and 18.